Hello, folks. Once again, we'll look at some more of Chapter 19. Probably finish it, honestly, and then we'll maybe look at some homework. So let's work with me here as I'm at the conference. Now, normally I don't like to go into the biochemistry aspects of organic, but this one's I felt important enough to spend a little bit of time to talk about amino acids. Amino acids. That amino acids are essentially contained the functional groups of an amine and a carboxylic acid. So, with then a R group attached to an alpha atom. So the generalized thing is the structure is we have some sort of an H one pair CHR C11OOH. And of course, these guys combine by a dehydration aspect of that to form an amide. And the only thing that makes one amino acid different from the other is the R group. Now, this is a chiral center. So it is possible to have two isomers, two enantiomers of this. The enantiomers get labeled either R and D. The L and D. The L is essentially the S isomer, and the D is the R isomer. However, the L isomer is the only one that exists in nature. Our body will only use the L isomer. Now, that's not to say there may not be aliens with amino acids out there that you will use the D, but the only thing that is in all of our Earth-based life forms, if it has amino acids, it's using the L isomer. Now, there's various groups, and the R groups get abbreviations both as three-letter abbreviations as well as single-letter abbreviations. I'm going to just the three-letter ones like glycine. Glycine just has the R as being the H. Alanine, which is basically a methyl going off. Phenylalanine, which is basically a benzyl group. C6H5. A benzyl group, essentially. Serine, which is essentially a methanol group. Cysteine, which is a methylthiol group. Methionine, which is essentially a ethylthiol group. Let's do the next line rather than try to glutamine, which is essentially a propanoic acid group. CH2, CH2, C double bond O, OH, and lysine, which is essentially a butylamine. So a 4-carbon chain followed by an amine group. Now there's others, but all these are some of our main ones. Most of our organic chemistry, we're learning about, how do you form this and what type of things do these guys do? these R groups can make the acid group organic in nature or polar in nature. We can have hydrogen bonding interactions. We can have thiol linkages. We can have all sorts of fun stuff. We have acidic and basic groups. So, gotta remember, in the amino acid, the NH2 group is basic, and their carboxylic acid is acidic. And while we can have this neutral, it's almost never neutral. In fact, it would rather exist as a salt. If it exists as a salt, then it's going to be with a high melting point and high water solubility. So, ability. Now, it's actually going to exist in what we call the Zwitter ion form. The Zwitter ion is in the case of here where we have where both sides are charged. H3 and C, carboxylate on the other side. That this is the neutral form that is present at about pH 6. Now, depending on this guy, in strong acid, the carboxylate gets pronated, and this stays pronated. In strong base, the amine gets depronated, the ammonium gets depronated, and that stays there. And since there are two different acidic regions, we have an isoelectric point that we can move. So we have a pKa for both acid sets for both. The isoelectric point is pH above which exists in the neutral form. So we're looking at what range we have a range on the pH scale. It's like all acid, all base, neutral. So this point we're looking at, these 2 points, is our isoelectric. What range is this essentially neutral? So we can actually measure, just like a pKa, we have a pi. Pi is the average of both pKa's. So if that has a pKa of 3 and that is a pKa of, well, I guess that'd be a pKa of, like, say, 9, and that's a pKa of 3, the average of that would be 6. So, but they're not going to be nice numbers. Average of both pKa's. So essentially, one plus pKa2, and that's how we could easily figure out that. So that's as far as we're going to talk about carboxylic acids. The rest of this chapter, which isn't honestly a total lot, we spent talking about nitriles. So a lot of our nitriles can be made via SN2. Via SN2 mechanisms. Substitution usually. Because nitriles react with nucleophiles by nucleophilic addition reactions. So that we can prepare these because cyanide is usually a pretty good nucleophile, but they'll react with nucleophiles. So here's some reactions of nitriles that we may see. Reaction 1, if I mix a nitrile with water and acid or water and base, it's going to either form carboxylic acid or carboxylate, depending on whether we treat this an acid or base. It's one reaction. If I do let's say 2A, if I do this with lithium aluminum hydride and water, goes straight to an amine. Well, it goes all the way to an amine. If I do this with a weakened, say like reducing agent like Dibol H, the diisobutyl aluminum hydride and water, I can stop this at a aldehyde. And if I treat this with a organometallic of some sort, if I treat this with an organometallic of some sort, like Grignard or like organolithium, this is water, I can get a ketone. So all that is magic, but we'll look at some of the mechanisms of what's going on. How are we essentially getting these guys? How are we converting a amine to an acid? How are we converting this C triple bond N to a C double bond O in these reactions? So let's look at these guys. So the in reaction 1, basically we're going to go at amide will tautomerize to amidic acid. But okay. So it's going to break it down into 2 steps. Step A, just to avoid the 1, we're going to have a nucleophilic addition followed by tautomerization and then B, we're going to go hydrolysis of an amide. Hydrolysis of an amide. Okay. So let's look at this. So let's start here with we have lone pair. Step 1, we're adding hydroxide. Say we're adding hydroxide then. Presence of OH minus. This is electrophilic carbon. And so carbon can only have 4 bonds, so we have to kick that out. So step 1 is to make and amido acid. Now we have now in the presence of water, because we're doing this in water, this guy's gonna take one of our protons from the water to stabilize the imide. Let's put another lone pair to make sure we can see that. Now we've reformed the base. The base is going to then deprotonate this. So this guy is, all this is pretty much reversible. So put that there. So the next step is, so we've deprotonated there. Now we have boom, 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 boom. So this lone pair can now swing back down and kick that out. Pretty much all these steps are, so we're going to actually, it has me doing this as one step. Deprotonating that, reform our base. So we have this NH2. So we've made an amide. However, in the presence of excess space, we keep on making these bases. Base can keep attacking. All these steps are kind of reversible, but what's the thing about reversibility is that by putting a lot of solvent and whatnot, we can shift this to one side or the other. One side or the other can shift by controlling the reactant, by controlling the solvent concentration. We can push it one way or the other. So kick that up. Once again. So the next. So we're formed so we have this. Okay. Now this can swing down, and we're going to, as I said, this is reversible. But in the presence of excess space, we can kick out the ammonia and kick out ammonia as a leaving group. And then, so we got this. So we formed an acid. Now, because this is present in excess base, and we have NH2 is not exactly a stellar leaving group, this has got to deprotonate this. And so, final step, which pretty much locks us in place, is a carboxylate. So, in presence of acid, mechanism is going to be slightly different, but the idea is we'll end with a acetate. But now we have ammonia, which is not a super good nucleophile. NH2 1 minus, yeah, that's not exactly super stable. NH3, not exactly going to keep attacking at this point. So once we get to this point, We just keep on pushing. Having that excess OH is going to push it that way as opposed to staying over here. Excess OH and excess water. Going to keep on pushing it to the right. So, or let's look at reaction 2. Just flip it over. Reaction 2. And what happens when we do it and then a strong reductant? How do we go all the way to an amine? First, how much do we go to an acid? So 2A, let's look at that. RC triple bond N. So if we have like aluminum hydride, we're going to attack here. It's a strong nucleophile. I mean, it's a strong electrophile, and we have a strong nucleophile. We're going to kick that over. So we have a RCH, double bond N, lone pair, lone pair. And this is going to then bind to aluminum hydride and stabilize this. Now, so it's kind of like how we saw earlier that most of these things can be stabilized in the presence of this is a Lewis base, that's a Lewis acid. Well, say a Lewis base, Lewis acid, and so that's going to attract that. So and oh. Sorry. So we stabilize that. Now that this is stabilized, we can now undergo further hydration. We still have more lithium aluminum hydride present. So I'm not sure if this is technically 1 step or 2 steps. We'll just do this as 2 steps. So kick that down. R, CH2, and then of course you have N minus. This might be 1 step, but then of course the aluminum hydride, and then so we're going to stabilize that again. I think I had in my notes this is 1 step altogether, but I have to look exactly. I might have just been lazy. But so right there we have, at that point, we have this incredibly weird, incredibly unstable. Well, we have a very interesting looking group right there. So this is what we have hanging around. It's kind of stabilized, kind of not stabilized in the presence of water. 2 equivalents of water. We're going to remove those groups, and we're going to have RCH2 NH2. And we're going to stabilize those guys as an OH aluminum hydrides. So in excess water, it's going to just push it that way. This is going to be the binding group to the aluminum. Now, if I have in the weakened version, it's how will this differ? How will this go? So RC triple bond N. We have the single age the aluminum with the R2, the dye ball. Put that there. Kick that over. So, starts kind of the same. Starts kind of the same, but now we add the water much sooner because we can't, because the aluminum is not going to necessarily accept, this aluminum is not going to act as good of a Lewis acid. It has those R groups on there. It's not going to be able to easily stabilize that amine. It's not going to keep reducing. It's not going to keep reducing. So instead, now when we add the water, we're going to add the water, it's essentially going to stop there. So the byproduct is, let's put this down. So RCH, and so we have an imide, except in the presence of excess water, this amide can keep being pronated. Keep being pronated. This is definitely reversible. So we have R, I'll just draw that like that, and H plus, and that, of course, has a resonance. I'm not sure we need to draw the resonance, but let's draw the resonance. Oh, and but from there, the base that we keep on forming can act as a Lewis acid, similar to a nucleophile, similar to the Grignard, and attack the imidocarbon, which is going to then kick that up and stabilize that. So at that point, let's keep going. R, we have an amine, we have an alcohol. Okay. And so as long as we still have water, we can force this to the right. So this, we can pronate this guy, and it can fall off and go backwards. Or we can pronate this guy. And oftentimes, this guy is more basic than the OH. So we're going to depronate the water to form ammonia, which is a better leaving group. So NH3 plus, but it's not going to just fall off right away. So in the presence of the base we just formed, going to depronate this. Those are going to kick up there, and that's going to kick that off as a leaving group. And that's how we form the the aldehyde. I know that's a very roundabout way. Very roundabout way. But so, both reactions, a strong reductant, that we form the imide first by putting a hydride onto the nitrile carbon and stabilizing it. And with the strong reductant, and then we add a second equivalent and stabilize it again. And then the water just makes it NH2. We no longer have and the OH is stabilized by the Lewis acid aluminum hydride. But in the weaker reductant, we only add one equivalent to hydride. And then we start the workup. And because the imide is not stabilized, we pronate that, and through a series of pronations, we can add a hydroxide and kick off the NH2 as a better leaving group. We have to pronate the NH2 to get there, but that's how we can go about that. I know it's a lot of really complicated stuff, but we can do that. Now, the third one and the last one, essentially the last one, is a lot simpler. A lot simpler. So regardless of whether it's Grignard or organolithium, the mechanism is the same. How do we form a ketone from there? So let's just do organolithium. Okay, so we're going to take this, it's going to attack there, and kick that up. So R prime, 1N, and then we work this up with water. So we're essentially following the exact same reaction mechanisms as in 2B. So when we work up with water, starts off protonating the imide. I'll go ahead and do the mechanism again, because protonating the imide. So we have NH there, R prime, and then still more water. We can then protonate that again. And so we now have a doubly protonated imide, which now is a very ripe for nucleophilic attack. Kick that up. And kick that up. So R prime, OH, NH2. Then that's capable of being pronated again. So R prime, OH, NH3 plus, and we're just waiting for a good excuse to kick that off. Now, last step, percent of base. Depronate that. Kick that up. Kick off a good leaving group. So exact same steps. Depending on where we're at when we start to work up with water. If we're in an imide form, water is going to push this to tautomerize into a ketone. If we're at a stabilized diamine, like a diamine, that the water workup is just going to protonate that into an amine, or like the doubly charged amine. So that is the chapter. It's not a very long chapter. So let's look at a little bit of this homework. Okay. There's a lot of questions I asked on here, but we'll see how actual hard they get. Okay, so propane dioic acid. So it's dioic acid. So propane, that's a 3-carbon group. Since it's dioic acid, means 2 acids. We're going to put that on there. So let's put a OH. Let's see. OH. O. And acid is always an ending group, so okay. I know exactly what I did wrong, and it's stupid, and I need to talk with them. So, for God's sake. That they just allowed me to put that wrong. So, they were very picky about that. So, naming and put that. Write the IUPAC name. So, how many carbon chain? 1, 2, 3, 4. So, it's a butane. Butanoic acid. So, we go lithium, butanoate. Then butanoate. Pretty simple. So, draw the structure of the acetic acid ion. So, okay. Acetate, that will mean. So, put it. Oh, let's probably want to put that and the charge and the O and the 2. That's probably what they want. Charge and electrons. Pretty straightforward. Consider the following 3 compounds. Rank these in order, increasing boiling points. So, the possibility of hydrogen bonding is always best. So, which one can have hydrogen bonding? This guy can have hydrogen bonding. This guy can have hydrogen bonding. This guy, the amide, has no NH bonds to hydrogen bond. So, that's going to be the lowest boiling point. But an acid is always going to be higher boiling point than everything else. What? Let's see. Okay. Well, I'd beg to differ, but sure. Okay. Least water soluble would probably be. Is it going to be this guy again? Yeah, I guess so. Personally, I would say the other guy, but. So, what equivalent. Okay, so we got to think about how do we form acids. The big hint here is ozonolysis. Ozonolysis breaks a triple bond into half. If you get 2 equivalents of the same thing, we're going to have, let's just draw this structure. And we got to mirror it with a triple bond. Ozonolysis. So I'm just drawing this in reverse. Because I'm going to cleave it in half. We're going to cleave it in half right down that middle. Let's see, what other things? Ranges carboxylates and increasing basicity. So we're looking at, okay, we have 1 fluorine, 2 carbons away, 1 fluorine, 1 carbon away, no fluorines. No fluorines would be the most basic. And 1 fluorine, 1 carbon away would be the, least basic. Because the likelihood of reaccepting that proton is what we're talking about. So far, I'm just knocking these guys out. Identify the base that can deprotonate this guy, 4.756. So we're looking for a pKa of higher than that. Boom. Boom. Nope. Boom. Done. Easy. So this first half I've knocked out in 3-4 minutes. Chicoric acid is found in basil and dandelions. Rank the labeled protons in chicoric. Ooh, okay, so acids are up. So B is obviously very acidic. I would say it's an acid. Anything that can be stabilized. Say D is maybe mildly acidic. Can this charge be stabilized? Then I think A, then C, but I'm not sure on that. So I'm guessing it's the other way around. See, then A. Okay. And it has to be how the charges are can be shifted around. But okay. Match the carboxylic acids and the pKa. So we have the higher the pKa, the less basic it is, the less acidic it is. So 1 chlorine, yeah. This guy is practically a strong acid. So far this hasn't been. Now let's look at, okay, hey, our fungi drawn in its neutral form. Oh, so we just need to, you need to redraw this. 2 equivalents of base are added to the positively charged. Gradually increased. 2 equivalents of base are, okay, so if it's positively charged to the, so 2 equivalents of base, so let's redraw that. The question is whether okay. The question is whether I'm just going to put things in here for now. Question is whether we do, since it's 2 equivalents, I'm going to say, I'm not sure if we have to put in the, I'll put in the electrons. So 2 equivalents at least is going to deprotonate that. So it's not NH3 plus. It's probably going to change that to 3, 1 minus. Now, the question is whether we deprotonate that as well. So we will figure that out right now. So it's probably O, let's see, triple one. So they want that to stay, and let's try the which. Okay. Okay, that's what I was afraid of. they're saying leave that protonated and those two get deprotonated first. Yep. Okay, so we have a nitrile is hydrolyzed amide and then goes to the acid. Show this hydrolysis under basic conditions. Okay. So I'll go ahead and do this mechanism. This is probably where I'll stop afterwards. Okay. Okay. Let's copy that over because this one will take a little bit of time if I'm to do this right. Let's see. OH. The lone pairs. I'm going to be. And put another lone pair on here. And let's see. Negative. So it says under basic conditions resulting in the amide intermediate. So how do I get to the amide intermediate? So let's now next we're going to draw some water. H O H. Okay, so this guy's going to then back here, and we're going to reform the there. So we're going to add a step. Okay, let's copy that down. Let's see. Okay, let's draw that. H, and let's delete. Let's see. Oh, let me delete that. Let's see. Delete that. Delete that. Okay, there's that. Okay, so now I'm going to protonate that again with water. Okay, so let's copy that. So I'm just trying to do this. Okay, okay. Go there. It's gonna H2, so let's go to the next add remove step. Okay, thankfully I can copy this down. It's making it a little bit easier. H, and we're gonna have plus, and I'm gonna delete that. Now we have OH minus. OH minus is going to then, we're gonna put some charges on this. And we're going to draw an arrow. We're going to kick that up. And actually, I'm going to delete that and redraw that with an OH instead. A separate H, so I can just better. So I can better do this. Okay, now drawing this, we're going to kick that there, draw that there, kick that up. Okay, and then add the step where we show the product. Okay, at this point, I should be good. So let's see, delete that. Go on there and delete that. And I need to put the lone pair back on there. Let's make sure that's what they're asking for under basic conditions. Amide intermediate. Let's try something different. Let's try this. Okay. I'm going to rearrange a step here. Instead, let's make that rearrange the order just to see if that is what they're looking for. Oh, let's see. So, in which case you'd have an acid base, acid base. Okay. So in this case, let's delete that. Okay. Put that there. That might make actually more sense. Okay, let's delete that. So we have NH2. Okay. Minus, and then, so we're saying water. It was like base, water, base, water. Okay, let's actually. So base water, where we switching back and forth, back and forth, back and forth. So, okay, then I draw the arrow, then we go, oh, it's deprotonating that. Then that goes, that could go to there. Let's try that. And then we'll see, did I do it wrong? Yeah, there we go. That's what they wanted. So, notice how I did switch it to base and then water, and then base and then water, because if we're moving some base, now there's, since it's base and water, the water reforms the base can keep reacting, and then that makes water byproduct, and the water can keep reacting, so it bounces back and forth, back and forth. Let's see, let's see if there's any major organic products. So you're just looking at like, oh, this is a strong reductant, so that's going to knock that all the way to an amine. Oh, sorry, yeah, an amine. This is a strong reductant. We're going to add ethyl there, and it's going to go to a ketone. Let's see. Strong reductant. It's going to go to an amine. Ozonolysis. That's going to split that apart into two acids. Two different acids, mind you. Ooh, borohydride. I'll maybe look at that one. I know I'm going over time. Oh, and plus I put in one of these. So, okay, what's my unsaturation index? Remember that nitrogen takes care of one of those hydrogens. So it's C4, essentially 4 minus 6 divided by 2, which is 3. So 4 minus 3 plus 1 means we have 2 degrees of unsaturation. We see the IR. Oh, what's that? That's a big jump. There's your CH stretches. That's a nitrile. I can tell you right there, it's a nitrile. You see a single peak right here. You don't see a matching peak, so there's probably not any double bonds. So that's another nitrile. We see a 1 hydrogen and 6 hydrogens. How do you get 6 hydrogens? 6 hydrogens is 2 methyl groups. The fact that they're overlapping means it's that they're probably identical. So 6 hydrogens and 1 hydrogen, that looks like a substituted isopropyl. So my substitute, I can do this run real quick. Substitute isopropyl. Let's make triple bond. Bam. There's my structure. That took me all of a minute. So let's look. Borohydride. Borohydride. What does that do? That adds an alcohol. I'm trying to remember. Alcohol to the I'd like to say it's normally we add the hydrogen to the least substituted position, but I'm thinking we add the alcohol to the most substituted position and the hydrogen to the least substituted, but boron works in reverse. It's an anti-Markovnikov. So we would, if I'm not mistaken, form this. And I'm going to double check. But once again, what you need to do is you can't remember these things off the top of your head. Create a little checklist of reactions that you might be expected to know. So you can go, oh, BH3, what does that do? Boranes do this reaction. Oh, okay, and I need to do, what's a B? So, in the presence of that guy, we need to fully oxidize that guy. Okay. So, I'm going to redraw this. It's fully oxidized. I forgot to do that. So it's going to form an acid. Eee. So how did I do that? How does the miracle mind work? I go borane. That I learned like 4 or 5 key reactions of adding alcohols across double bonds. Borane, because boron is less electronegative, it works in reverse. The boron adds where the hydrogen would add, and the hydrogen adds where the alcohol would add. And then the peroxide kicks off the boron and replaces it with the OH. And then chromate just oxidizes things. So that's just an example of how I do that. How that's an oxidizing agent, and it's going to keep oxidizing. But create a checklist of reactions. If I see this, these things react. If I see this, these things react. Chromate. If I have an OH, we're going to oxidize something to an aldehyde or a ketone or an acid. So the fact I added chromate means I'm probably going to have an alcohol. This is one of the many ways we're going to add an alcohol over a double bond. So, okay, that is that. I will see you when I return from the conference.